with confidence intervals. The formula for a confidence interval with two proportions is p hat 1 minus p hat 2 plus or minus z times the square root of p hat 1 times q hat 1 over n1 plus p hat 2 times q hat 2 over n2. To interpret a confidence interval, we'll use a statement along the lines of, we are 95% confident that the true proportion of dogs is blank to blank higher or lower than the true proportion of cats. We are 90% confident that the true proportion is this. We're saying that we are 90% confident that the difference between the two proportions is these values. Once we get to hypothesis testing, you'll notice that our final p-value is interpreted using the same idea, that we focus on the difference and what that means instead of the actual true proportions. When we do hypothesis testing with two proportions, we care about whether the difference between the two proportions is statistically significant or unusual. This is the only hypothesis testing where you will pool in order to find the standard deviation. An easy way to remember that is you wouldn't want to be in a pool with somebody who's really unusual or weird, just like you're trying to find if the difference is unusual or weird. To go over hypothesis testing for two proportions, we're going to go over number 18 in your book. This is on page 521. A study published in the Archives of General Psychiatry in March 2001 examined the impact of depression on a patient's ability to survive cardiac disease. Researchers identified 450 people with cardiac disease, evaluated them for depression, and followed the group for 4 years. Of the 361 patients with no depression, 67 died. Of the 89 patients with minor or major depression, 26 died. Among people who suffer from cardiac disease, are depressed patients more likely to die than non-depressed ones? For hypothesis testing, we will use phantoms. So first, we'll start with P. P1 will be the percentage of patients with depression, and P2 will be the percent of patients without depression. H will be our hypothesis, so H0 will be P1 minus P2 equals 0. This means that there is no significant difference between the two. Because of that, this will be our H0 for every problem that we see like this. Our alternative hypothesis will be P1 minus P2 is greater than 0. This means that a higher percentage of patients with depression died than the percentage of patients without depression. If your problem just asks whether there's a difference between the two proportions and not whether one is higher or lower, then you'll do not equal to 0, which I'll talk more about later. Next, we have assumptions and conditions. Our first condition is that both samples are random. In this problem, it doesn't say that the patients were found randomly, so we can just assume that they represent the whole population. Our next condition is that each sample has to be less than 10% of the entire population. Looking at the numbers, we can assume that this is the case, as our samples are 361 and then 89. Our third condition is that there must be at least 10 successes and 10 failures in every sample. For this one, you have to do a little bit of math, but it's not that hard. For our problem, it's easy to look at the numbers and know that all of our p-values are greater than 10. From there, you can calculate Q and know that those are also greater than 10. In examples where they just give you the proportion and not the actual numbers, you have to calculate it. So you'll take the proportion and multiply it by your sample size, or n, to make sure that both your successes and your failures are greater than 10. Finally, the last condition says that both samples have to be completely independent from each other, which means that the outcome of one sample cannot affect the outcome of the other. For this example, you can read the problem and know that one patient in one group is not going to affect the probability of another patient in the other group having depression, so we're all good. For n, you just have to name the test that you will be using. For our example, we are using a 2-proportion z-test, because there are 2 proportions, and you know that if it's a proportion, then you're going to be using z-tests. T is where you calculate your test statistic. For 2-proportion z-tests, you have to be a little creative. First, you'll find your p-hat 1, and then you'll find your p-hat 2, and then you'll subtract p-hat 1 minus p-hat 2 to get your overall p-hat. Then onto O, where you will find your p-value. With proportions, you always start O by finding mu. With 2 proportions, we know that mu is going to be 0 because we're looking at the differences between the 2 proportions, so this will be the case with every one of these problems. Then, after finding mu, we have to find our standard deviation. This is where we're going to find p-hat and q-hat pooled, and then use that to find our standard deviation. To find your standard deviation, you'll take the square root of p-hat pooled times q-hat pooled over n1 plus p-hat pooled times q-hat pooled over n2. To get p-hat and q-hat pooled, it's very simple. For p-hat, you'll take your successes of 1 plus your successes of 2 over n1 plus n2. And then for q-hat pooled, you'll do the exact same thing, but with the failures instead of the successes. So let's do this with the problem we've been working on. First, we'll start by finding p-hat pooled and q-hat pooled, and then plugging everything into the equation. When plugging the formula into your calculator, I like to store numbers in variables in the calculator so that you don't have to round throughout the entire process. To do this, you just have to find the value and then hit store and then alpha and then pick whatever letter you want to store your number into. For this example, I stored p-hat pooled times q-hat pooled in A. Under the square root, I did A divided by n1 and A divided by n2, and I stored both of those values respectively into B and C. From there, you just have to add B and C and take the square root of both of them, and you have your standard deviation. Now for the most important part of phantoms, O. This is where you'll find your p-value. You'll start by drawing in the normal model. Here you can write in mu and the standard deviation. Then you'll write in your new p-hat, which you found back at letter T. Then you'll use that value to calculate your z-score by taking your new p hat minus mu over the standard deviation. I found a z-score of negative 2.213, which is very low. Looking at the drawing, clearly I did not draw it that low. That is where looking at the standard deviation is important. So I went back to correct it. On your calculator, you'll go to Stat, and then Tests, and then go to number 6 called 2 Proportion Z-Test. Here you'll plug in the individual p-hat values, so your successes for each proportion individually. And then you'll also plug in N1 and N2. I got a p-value of 0.987, which compared to 0.05 is very statistically significant. To interpret this p-value, I'm going to start by rewriting out our initial populations and our hypothesis. Since our p-value was significantly higher than 0.05, we are going to claim that we fail to reject H0. Although we are not 100% certain, our p-value gives us strong evidence that H0 is true. So, this means that there is not a strong difference between the two proportions. So, our final statement will read, we have strong evidence that depressed patients are not more likely to die than their non-depressed counterparts. If, when writing our hypotheses, we had determined that our alternative hypothesis was P1 minus P2 is not equal to 0, then we would have gone about finding P a little bit differently. When drawing your normal model, you'll draw the p-hat value the same way that you did in our example. However, you also repeat it onto the other side. Then, when you find your actual p-value with your calculator, you just multiply it by 2 and use that to compare. Finally, your statement would reflect that there is a difference between the two proportions, even if we don't know exactly what it is.